A big Zoom crowd today. Okay, put in the chat if you can hear me. Okay, I'll switch to my headset soon. Let's get some music going. All right, let's start with attendance. So if you weren't here yesterday, the way it works is this is group A, group B, group C in the back, group D in the back right. And then row numbers is row 1, row 2, row 3. Then seat number is how far are you from the left of your group. So you're seat 1, you're seat 5. Then I got the hand sanitizer again. And if you weren't here yesterday, this comes out pretty fast. So don't squeeze it, just tip it over. Wash your hands with it if you want. That's just in case we have to do contact tracing. The attendants will allow them to be able to do that. All right, I'm gonna get the headset set on now. Okay. Can you guys tell me if you can hear me again? I got my headset on. Cool. That's good. All right. So I think we're good to go. Start class. So starting off where we left off yesterday, when we're talking about that average velocity of the basketball, we'll go back to there. And now that we're getting into the calculus material, I'm going to try to start every day with learning objectives. So just like on the syllabus, how they're learning objectives, maybe you don't know what the words mean yet, but this is more of something by the end of class, you should go back to it, and I'll try to remember to go back to it at the end of class, and you should check these off, and yes, I understood it, I'm able to do these. I try to use these active verbs like distinguish or calculate. They're active, not passive, so you should be able to do these. And if you're not able to, that means you need to come to my office hours and figure that out, and I can help you. Okay. So learning objectives, distinguish or differentiate between secant lines and tangent lines. So we'll talk about what those mean, and you want to be able to distinguish between the two. And likewise, we want to distinguish between average velocity and instantaneous velocity. We talked about that a little bit yesterday. We'll dive into it a lot more today. And then we want to calculate all four of those. So secant lines, tangent lines, average velocity, and instantaneous velocity. So those are learning objectives. We'll come back to at the end of the class. All those words will make a little bit more sense, hopefully, and you should check off if you are able to do that or not. So the first half of the class, I'll talk about the theory. Second half, we'll do half your homework on WebAssign. Half sounds like a lot, but you only have 4 questions on your homework. That's due, I think, Friday. So we'll do 2 of the problems, and then you have 2 to do on your own. Okay, let me make sure I pull up the chat over here again. Okay. So this is where we left off yesterday. This was an example of displacement in time. So the y-axis was the height of a basketball, and the x-axis was really the t-axis, the time axis. I'm just going to turn the lights down real quick. Okay, I'm back. So that we have the height axis and the time axis, and you can see we are at a height of 10 at the very top, because the basketball hoop has 10 feet of height. And then we're looking at a point in time, 0.5 seconds later. That's the x coordinate, or the t coordinate in this case. 0.5 seconds later, what's the height of the basketball? Well, it's 5.975 feet. Okay. And then we started talking about what happens if we connect those 2 points by a line. So if we connect these 2 points, I'll try to do that here. Okay, if we connect that with a straight line, and we want to talk about its slope, that's why we're going over the slope, point slope form and the slope intercept form. We really care about the slope. What is the slope interpreted as? Well, slope is a rise over a run. And in this case, the rise is a change in height. So I'm going to put a delta or a triangle for change in height. And the run is a change in time. So let me use a different color here so we're not all red. Okay, so we got this change in height. That's the rise, so delta H. And this right here is the lapse time from when it kind of rolled off the basketball rim and 0.5 seconds later. So that's a change in time. And so if we have a change in height over a change in time, that's a displacement divided by a change in time. That's going to be a velocity, has units of velocity, and that'll be units of feet per second. And feet per second is a velocity. Okay, so this is a good spot to talk about average velocity versus instantaneous velocity. So average velocity, all it is it's a change in position over your elapsed time. So for example, if I walk to the back of the classroom and then back to where I'm sitting, and that took me 10 seconds, my average velocity would be 0 because my displacement's 0. Now my speed would be something different because speed is defined as the total distance divided by your time. So say if it's 50 feet there and back, and it took 10 seconds, and I'd have gone 5 feet per second on average, and that would be my speed. But if I'm talking about velocity, velocity is a change in displacement. So let's write that down. So velocity, and we'll say specifically an average velocity, that's a change in displacement over the elapsed time, the change in time. Actually, displacement is a change in position, so it'd be better just to say a change in position right here. And change of position is displacement, just to be a little more accurate with the meanings of our words. So a change in position over a change in time, that's average velocity. Speed, the meaning of that is the total distance over your elapsed time, and we'll call that average speed again. So the difference is, say I happen to, if I died in Kalamazoo, Michigan, which is where I was born, my average velocity over my whole lifespan would be 0 feet per second, because my change in displacement over my whole lifespan would be 0, I will say miles, maybe, if we're gonna be precise. Miles would be a little less precise. So if I died where I was born, my average velocity over my whole lifespan would be 0. That wouldn't be my average speed, because speed is talking about my total distance, and I've definitely traveled more than 0 feet throughout my whole life. Does that make sense? Difference between average velocity and average speed? Okay. Kind of a cheesy example, but all right. I think we can move on. Oop, not yet. Okay. So we really don't care that much about average velocity. We really want to talk about instantaneous velocity. And instantaneous velocity is asking the question, what is my velocity at 0.5 seconds? It's not saying over an interval of 0.5 seconds like we're doing before, but let's say specifically and particularly at 0.5 seconds, what is my velocity? I don't care about the time values around it, just at that specific point. So that's an instantaneous velocity. It's at that instant, how fast am I going? And to go into that, I'm going to stop sharing here and go back to the plot we had the other day. Okay, so there's that plot. I took a screenshot and put it on the PowerPoint. And there's my line connecting those 2 points. And I had a little trouble yesterday changing all these zeros to a different number, but I'll do it one more time. I think I just made a mistake yesterday. So let's change our point, and let's just call it time value A, and then we're going to define A to be some number. So let's change this to A. Change this to A. Maybe A equals 0.4 seconds. We'll change this 0 to A, that to A. And then this, remember, this is our point slope form of our equation of a line between those 2 coordinates. Now let's define A to be something. So we can actually just make a slider. Let's say A equals 0.4 first. And we can make a little slider. Let's have A go from where we started before at 0 seconds. So let's start at 0. And let's get really, really close to 0.5 seconds, our other coordinate, say 0.49. And we'll increment our little slider by 0.01. Okay. So I made a little slider for me. We'll go back to where we were before. That's when we're at time value.
Officer, we can't see the screen.
Oh, thank you so much. Forgot to share my screen. Okay, sorry about that. All I've done is what I was trying to do yesterday when I changed all the time values of 0, and I changed it to A. So I changed it right here. I changed this 0 to A, this 0 to A. I changed my point slope form, those zeros to A, and A equals 0, so it's back to where we started. We're looking at the 2 points when the basketball is on top of the rim and the basketball 0.5 seconds later. Okay, now let's have our time value for our first coordinate get closer and closer to a time value of 0.5. And all these slopes of these lines are average velocities. So if we take the slope of this line, it'd be an average velocity. If we get closer and closer, this line is approaching what we call a tangent line. So we can get really, really close. It's an average velocity that has a very small time elapse. We can go a little further away. And all these lines are called secant lines. And as we get our change in time smaller and smaller, they approach our tangent line. Okay, so let's go back to our notes. And I'll share over here. Okay, go back to our notes. And a secant line, going back to our picture. If you pick 2 points on some curve and draw a line through it, that's a secant line. And then secant comes from the root word secans. That's Latin for cutting. So that's why they called it secant line, because the secant line cuts through a curve. Okay, I'm gonna check the chat, see if there's any questions. Okay. A tangent line comes from tangents. That's Latin for touching. So that's why we call it tangent line, because a tangent line, if we pick that point over here, it's just barely gonna touch it. It's only gonna touch it in one spot. It's not the best line right there. So it's just barely gonna touch it. That's a tangent line. And the relationship between a secant line and a tangent line, and that's the important part for today. So the relationship is that the tangent line is what the secant lines approach as the run approaches 0. Run referring to rise over run. So as we make our run really, really small, our secant lines will approach this tangent line. And the reason why this is important physically is secant line corresponds to average velocity when you're talking about the slope. So this is going to be the slope of the secant line. And that's what we're doing in that earlier example. When we went from 0 seconds to 0.5 seconds, that was a secant line. And we're looking at the slope of it. It's a change in height divided by a change in time. That's a slope of a secant line. That's an average velocity. And then the tangent line corresponds to instantaneous velocity. So the slope of the tangent line is instantaneous velocity. Any questions so far? Any questions on the chat? So the goal for the next little while, and the goal today at least, is going to try to approximate slopes of tangent lines. And those are going to correspond to instantaneous velocities, the velocity at an instant. So we're only going to be able to estimate those today. Later on, we'll be able to exactly calculate them, the exact instantaneous velocity. And it doesn't always have to be velocity. It could be any kind of rate of change. It could be a volumetric flow rate. It could be how much cheese you eat per day. Any kind of rate per change. Okay, any questions? Okay, I don't see any questions in the chat. All right. So before we get to the homework, I'm gonna go back to my computer and try to give you a little bit more intuition about slopes at an instant, because I think before all you guys have done is slopes of a straight line, and that's it. So what does it mean to take the slope of a curvy line? So let's look at that a little bit more. Look at some more graphs. Okay. So what does this look like? Oh, let me make sure I'm sharing my screen. Share screen. Okay. And pull up the chat again. Cool. So what does that look like? What kind of function? Straight line? Are you sure? Okay. So let's zoom out a little bit. Someone said linear in the chat. I tricked you. It's actually a circle. All right. What's this function look like? Looks like a parabola. Let's see. Okay, that's sine of x. Let's do one more. No one wants to say it's linear anymore. So, anybody want to think this one's linear? Raise your hand if. Okay. This one's a weird. It's not even a function. It doesn't pass the vertical line test. I'm not even sure what this is. It won't show me my equation anymore. There is some messy sine and cosine stuff. But anyways, the whole point of this is that if you zoom in far enough to any function, almost any function, we'll talk about the exceptions in a minute. If you zoom into any function, it'll start looking like a line. And that's a good thing, because we know a lot about lines from what we know from before. We know how to take a slope of a line. So if you zoom in far enough, it now looks linear, and we can start talking about a slope at that point. If it was just a straight line, then we can say, oh, the slope at this point is 3 or -3, something like that. And that's going to be the whole concept for about a week or two, is we're going to zoom in far enough, just like how I was bringing those 2 points closer and closer together. Really what we're doing is we're zooming in far enough. Our function now looks like a line, and it essentially is a line. And as you have your run, the rise over run, as you have the run go to 0, it does pretty much turn into a straight line. And then we can talk about slopes And those slopes, when you zoom in far enough, now we're talking about instantaneous velocities or instantaneous rates of changes, and apply it to any kind of application you want. Okay, so that's the big idea, is when you zoom in far enough, it looks like a line. Okay, any questions there? Okay, we're making pretty good time. Just to give you guys a quick mental break before we move on to the homework, let's watch a sports blooper and make sure I share my sound for you guys. Oh, you know what? It'd be better if I just switch to chat box.
What? Oh, no. Oh, yeah. Forget about the $90 fries. Are you kidding me?
All right, I got this one.
I got it. Oh, no. And the dog.
Well, he did get the ball.
What?
That's the same guy. This goes really serious business.
And the same guy.
It's the same guy.
Same guy's ticked off.
He lost his first meal, and then he just lost his second meal.
One away from Verdugo, swings it. It's a fly ball on her right. And going back is Borenstein. The ball is off his glove and over the fence for a home run.
Actually, the ball bounces off the outfielder's head and over the fence.
You turned it into throw. You made it worse. That's gotta hurt. I don't know what the odds are of losing your food twice in a row in the same game. Okay, let's start the homework. We learned all the theory so far. We made the distinction between tangent line and secant line. Tangent line just barely touches the curve. Secant line cuts through it. Tangent line corresponds to instantaneous velocity, and secant line corresponds to average velocity or average rate of change. Okay, so that's all the theory for today. Let's start actually doing problems. Okay, so I think this is question number 4 on your homework. I think this is probably a good one to start with, even though it's the last problem on your homework, because I think it gets at the idea of we're approaching a run of 0 in this problem. And then we'll approximate instantaneous velocity a little bit differently in the next problem, but this is a good one to start with. Oh, and you guys can't even see it yet. So let me share my screen. You guys are gonna have to hang in with me. I'm still getting used to switching around all the time. Okay. So the displacement in centimeters of a particle. So it seems like they use particle when they don't know what they want to talk about. Or in physics, are any of you guys in physics this year? Yeah. So sometimes you just talk about particle when you're not worried about the rotation of a rigid body. So if it's like, I don't know, if you're not worried about the rotation because that effect is negligible, then you can just talk about a particle and it'll do the same thing, almost the same thing, because the rotational effects are negligible. Yeah, if there's no friction on the surface, things like that. I know in mechanical engineering, if any of you guys are in that field, once you take dynamics, you stop talking about particles, you talk about rigid bodies, and that's when you actually take into account the size of the thing and the rotation of the thing. So, yep. So either they don't know what they want to talk about, or they just want to simplify the problem in this problem. So we have a particle that's moving back and forth along a straight line, and it's given by the equation of motion, S. So S is just the output Does anybody get freaked out when it says S instead of Y? No? Okay, that's good. You should be able to interchange letters. It's just a name for something. It's a name for the output. We like to use Y, but sometimes it's S or some other letter. So the output equals 3 sine of pi t, pi times t, plus 2 cosine of pi times t. Now I bet some of you are going to ask me on Ask Your Teacher on WebAssign, why are you getting this wrong? Well, make sure your calculator is in radians and not degrees. So if it's not in radians, go ahead and do that right now. That'd be a little upsetting if that's the reason you're getting it wrong, if you knew the concept, but your calculator was just in the wrong mode. Okay, so find the average velocity during each time period. Average velocity should make you think of slope of secant lines. What's a secant line? That requires 2 coordinates on your curve. Our curve is this S function, this sum of trig functions. And what do they give us? They give us a time period, and that's so it's an interval. Like when we're doing intervals for domain, they give us an interval for a time period. They're saying find the average velocity going from time equals to 1 second to time equals to 2 seconds. Okay, I'm going to start writing now. So let's calculate our rise. Rise is equal to S of 2 minus S of 1. So that's the rise. And then what's the run? Anybody? What's the change in time here? So we go from time equals 1 to time equals 2. So it'd just be 1 second. Then the rise is a little bit more complicated. Just for this very first problem, I'll write out the whole thing, but then from there on out, I'll just write S of something, subtract the 2. So what is S of 2? Well, we plug in 2. So 3 sine of pi times 2 plus 2 cosine of pi times 2. Okay, so that's S of 2. Then we subtract, and notice I'm going to put big parentheses here because there's going to be 2 terms we're subtracting, and we need that minus sign to distribute to both of them. We're subtracting the whole thing, not just part of it. So I'm subtracting when I plug in 1, 3 sine of pi times 1 plus 2 cosine of pi times 1. And end my big parenthesis there. All right, so that's going to give you some number. And it actually ends up giving you 4. I calculated it before class. So the rise over the run equals to 4 over 1. So it's going to give you 4 centimeters per second. And they just want you to put a 4 right here. They already put the units there for you. Okay, any questions on that? We're calculating a slope of a secant line. The slope of a secant line gives you average velocity. Notice the units. The rise is in units of centimeters. Did they say that in, yep, the displacement in centimeters. So that's the S. And then T is the time in seconds. So displacement is in centimeters, which is the rise. The run is in time. So you get centimeters per second. That's the average velocity. Okay, let's keep going. So part 2, we'll switch colors. I'll just right away say our slope, or our velocity average, is going to be S of 1.1. So plug in 1.1 into your displacement function. Subtract when you plug in 1 into your displacement. Now you got a new run. The new run is 1.1 minus 1. And notice how I keep the 1.1 terms on the left and just the 1 terms on the right. You can switch them, but you got to switch both so it's consistent. All that matters is consistency. Not necessarily that one always has to be on the left and one always on the right. You could do S of 1 minus S of 1.1 divided by 1 minus 1.1, give you the same exact answer. Okay, any questions on the chat? Nope. Okay. All right, let's do, oh, we can say what this equals. Also, sometimes WebAssign is supposed to give everybody different numbers. Usually they're in red, so this might be a different problem than you have slightly. So don't just copy this because you might have a different problem. And this ended up being negative 8.2916. Okay, let's do this one. I'll change colors again. M is equal to, in this case, S of 1.01 minus S of 1 over 1.01 minus 1. So again, that numerator, I'm just plugging in those two time values, 1.01 seconds and 1 second, into my displacement function. So you actually got to calculate the sine and cosine stuff. This ends up being negative 9.3245. What do they want you to round to? 2 decimal places. So you really don't need these, those right there. And then the last one. M is the slope of the secant line, which corresponds to the average velocity. Yep. So these are in centimeters per second. Exactly. So geometrically, it's a slope. Physically, it's a velocity. Yep. So that's 2 ways to interpret it: geometrically and physically. And lastly, we've got S of 1.001 minus S of 1. 1.001 minus 1. That's equal to negative 9.41. Okay, so what have we done going from part 1 to part 4? Got more exact, how? Yep, exactly. So the 2 points defining the secant line are getting closer and closer together. That makes our run smaller and smaller. And that's what we're talking about when we zoom in far enough into any kind of smooth plot. It looks linear. And then we can talk about a slope. And so what's happening is we're approaching our tangent line. These secant lines are approaching the tangent line. And tangent lines we associate with instantaneous velocity when we talk about the slope of the tangent line. So part B says, estimate the instantaneous velocity of the particle when the time is equal to 1. So what do they look like they're approaching? These slopes of the secant lines kind of look like they're approaching something. I'd say they're approaching about negative 9.5 centimeters per second. Okay, that's a little bit arbitrary. You could have said negative 9.42, negative 9.45. WebAssign will take it as a certain tolerance. Something that you could do to be maybe a little less ambiguous is just do this again, but let's do 1.000001, and that will get you pretty close to what the instantaneous velocity would be instead of just guessing. Yep, exactly. So just get a very small number away from 1. Yep. Yeah, yep. So later on in about a week or 2, we're actually going to have an equation that tells us exactly, without guessing or plugging a very small number in, what the instantaneous velocity is. Is there a question back there? Okay. Any other questions? So just for today, if you do a guess, it's going to be okay with it. The main idea is these numbers, they look like they're approaching something around negative 9.4s, close to negative 9.5. We went from negative 8 to negative 9.3, then we only increased by 1/10, and so the change is getting smaller and smaller. So we're approaching some output value. some velocity value, which would correspond to our instantaneous velocity. Okay, no questions on the chat yet. All right. So what time is it? We got another 10 minutes. Okay, got one more problem. I think this was the number 1 on your web assign. Can you guys in the back hear me okay? Yeah, okay, cool. And the Zoom thing's in the way. All right, so a tank holds 1,000 gallons of water, which drains from the bottom of the tank in half an hour. The values in the table show the volume V of water remaining in the tank after T minutes. So they give us a little table. The top row is time. The second row is volume in gallons. If P is the point 15, 245, so what that means is they're talking about this one right here. Uh-oh. This one right there. So at time 15 minutes and 245 gallons, that's the point P. On our graph of V, so what they mean by graph of V is if you plotted these data points, it'd look like some kind of function. Maybe you could connect the dots with a line. So connect the dots. Find the slopes of the secant lines, PQ, when Q is the point on the graph with the following values. So this one is point P, and these ones over here are point Q. And secant lines, you need 2 points, and they're calling that P and Q. So our 2 points are P and Q. We're going to calculate the slope of the line PQ that connects the points PQ. All right. So, and if we're doing slopes of secant lines, the slope of the secant line is a geometric interpretation. The physical interpretation is it's the volumetric flow rate. So it's a gallons per minute. It's an average volumetric flow rate. When we get to part B, the slope of the tangent line, that'll be instantaneous volumetric flow rate at time equals to 15 minutes. So that's the physical interpretation, but the geometric interpretation is this: we're doing slopes of secant lines and tangent lines. Okay, so how do we find the slope? For the sake of time, I'm just gonna do two of these parts. And I'm gonna do it in such a way that we can do part B after. Let's see, so part B wants us to find the tangent line averaging the slopes of 2 adjacent secant lines. So our point P is 15,245. Exactly, so I'm gonna do these two right here, because those are adjacent to time equals to 15 minutes, and that'll be enough information to solve part B. So I don't wanna do all of the parts just for time's sake, but if I do these two, we can also answer part B afterwards. And I'll explain a little bit more on that. So any questions in the chat? Not yet? Okay, so let's calculate a slope. What's our output this time? Instead of position or displacement, this time it's volume. So we're gonna let's start with P. So let's start with P, 245 minus, and then we're gonna do this guy, 441 over time value of 15 minus 10. So notice I had my P points on the left and the Q points on the right to make it consistent. So 245 correspond to P, and 15 minutes correspond to P. And I don't know what that equals, but I'm gonna let you guys calculate that. And that would be the slope of that secant line when you're going from P to Q. All right, let's do this one now. I'll do a different color. So we're gonna do 245 again. minus 115 over 15 again minus 20. And that equals something. Are these going to be positive or negative? Negative, yep, because the numerator on the first problem is going to be negative, and the denominator on the second one is going to be negative. So it's both going to be negative. What's the physical interpretation of that? The water's flowing out of the tank. Exactly. So we're losing volume. We're getting less and less volume in the tank. So the rate of change of the volume per time is negative. So a negative is interpreted as it's leaving the tank. So if you get a negative, don't worry about it. Okay, so in this example, we're not making our runs smaller and smaller in this case. They want us to average our two adjacent slopes. And the idea is, I'll draw a little picture, maybe our parabola from before. So before we're kind of estimating the velocity right there. Well, if I pick 2 points on each side of it, 2 adjacent points, and make secant lines like that, the average of those two slopes will be the average of, the angle would kind of compromise. So it would be something like this, which would be pretty close to our tangent line slope. So that's the idea. We're picking 2 adjacent points, average the slope, and that should give us a pretty good estimate on the tangent line. So I'll draw that in a different color. Nope. Right. It's not always the best technique. You gotta kind of know what your plot looks like to see if that would actually work. So the idea is if we pick 2 secant lines around it and average them, they should look like our tangent line. And so I'm just gonna say, we'll call this one A and that number B, whatever your answers are. This one you get by A plus B over 2. You're just gonna average them. And that'll be an approximation to your instantaneous volumetric flow rate. Okay, how much time do we have? Got 5 minutes. I just want to show you one thing before we end. I forgot to tell you about the exception of when you zoom in far enough it looks like a line. So we'll do that right now. Anybody have an idea of a function that when you zoom in far enough, it doesn't look linear? Anybody in the Zoom audience? Anybody on Zoom know a function that when you zoom in far enough, it still doesn't look like a line? A what? A fractal? Okay, maybe. Can fractals be represented as a function? I don't know. Maybe. Something trig? Maybe, yep. Oh, that's a good one. So piecewise function. Yep. I'm gonna put one here. Okay, absolute value of x. That function, if we zoom in, it's always gonna look like a corner. Okay, zoom in forever and ever. Yep, anywhere else you can zoom in and it looks like a line, but specifically at x equals 0, it looks not linear. Yep. Well, we don't know what differentiation means yet. Yes. Okay, so piecewise is also good. You could have like a jump discontinuity. That's also true when you zoom in far enough, it might not look like a line anymore. And so that means we can't really talk about instantaneous velocity there anymore. That's what it means. So it's not a slope of a tangent line. If you try to make a tangent line just touch it, well, if you put a line against it, it would kind of rock along that corner. So which line would be the tangent line? So that's kind of the idea there. Okay, it's really nice outside. You guys can go. Thank you for your Zoom audience here too. You should go outside. It's nice out.
Is that function homework, is that optional or is that graded homework?
Nope, you have to do it. Well, you don't have to. If you want the points, you should do it.
Yeah.
Yep. Do it tonight at midnight.
Have a good one.
Yep, you too.
Thank you.
Might as well.
Were you here in first day class?